the heat you feel, and the electricity you use. So think about this for a second. You stick a metal spoon in your hot coffee, and bam, the handle is hot almost instantly. And that same kind of metal, it's exactly what we use for electrical wires. So is that just a total coincidence that the best things for moving heat are also the best for moving electricity?
Well, it turns out it's not a coincidence at all. In fact, it's a deep and pretty elegant principle of physics that was figured out way back in 1835. It's called the Wiedemann-Franz Law.
Yeah, this law gets its name from two German physicists, Gustav Wiedemann and Rudolf Franz. They were the ones who first really dug into this, and they noticed the surprising pattern. For all these different metals, the ability to conduct heat and the ability to conduct electricity seem to rise and fall together, almost in perfect sync.
So what exactly did they connect? To really get what they discovered, we kind of need to look at a tale of two different types of conductors.
So on one side, you've got thermal conductivity. That's represented by the Greek letter kappa. It's just a fancy way of saying how well something can move heat from one place to another. And on the other side, you've got electrical conductivity. That's sigma, which, you guessed it, measures how easily an electric current can flow through. On the surface, these seem like two totally different jobs, right?
But here's the beautiful part of the Wiedemann-Franz Law. It reveals that these two jobs are not so different after all. In fact, they share a common cause, and it all comes down to the secret job of one tiny, fundamental particle.
And that secret ingredient, the one thing that's responsible for both of these things happening in metals, is the huge population of freely moving electrons just zipping around inside the material.
You see, these free electrons are like the workhorses inside a metal. As they move, they carry an electrical charge, and that's what we call an electric current. But at the same time, they're also carrying kinetic energy, which is what we feel as heat. So the exact same particles are doing both jobs. I love this analogy. Think of them as these tiny multitasking couriers, carrying two different kinds of packages, electricity and heat, at the very same time.
Now, this connection isn't just some vague idea. It's so consistent, so reliable, that it can be described with a surprisingly simple and, honestly, beautiful mathematical formula. So let's take a look at the law in numbers.
Okay, here's the core idea. The law basically says that if you take a metal's ability to conduct heat and divide it by its ability to conduct electricity, that ratio is directly tied to its temperature. To put it simply, as a metal gets hotter, how well it conducts heat changes in a very predictable way compared to how well it conducts electricity.
And this is where physics just gets so elegant. The entire law boils down to this simple equation. Kappa divided by sigma equals L times T. That's it. Thermal conductivity over electrical conductivity equals some constant, L, multiplied by the temperature. It's a profound physical truth captured in just a few symbols. So what's that mysterious L in the equation? Well, that is the Lorentz number. It's what we call the constant of proportionality. It's kind of like the magic number that makes the whole equation work. It's the thing that keeps the relationship between heat, electricity, and temperature so consistent for lots of different metals. But, science is all about understanding the details and the exceptions. And like a lot of laws in physics, this one is an excellent approximation, but it's not a completely unbreakable rule. So it's really important to know when and why the law breaks down.
So where does it get a little fuzzy? Well, first off, that Lorentz number, L, isn't perfectly constant for every single material. It can vary a little bit. Second, the law works best at really high or really low temperatures. In that middle range, things can get a bit more complex and the law becomes less accurate. And finally, here's a weird one. In super pure metals at very low temperatures, something else happens. The electrons can travel much farther without bumping into stuff, which actually causes both heat and electrical conductivity to increase as it gets colder, which is a little quirk the basic law doesn't quite capture. So after all that, what's the big takeaway here?
It's that these two worlds we thought were separate, the hot spoon and the electrical wire, are actually deeply, fundamentally linked by the behavior of just one particle, the free electron. And this isn't just some cool piece of trivia. Understanding this link is absolutely crucial for material scientists who are designing everything from computer chips to parts for spacecraft, where managing both heat and electricity is everything. It's just a powerful reminder that sometimes the most complex things have really simple shared origins.
And that really leaves us with a final big question, doesn't it? The Wiedemann-Franz Law showed us a hidden connection that we can literally see and feel every day. It just makes you wonder, what other invisible rules and hidden connections are out there, governing the world all around us, just waiting for us to find them?